Okay, this is how the electrostatic field and the magnetic field ultimately relate to each other and to electromagnetic radiation, which is to say light. This is worth a lot of extra points in physics and in life. Okay. Okay, at the fundamental level, I mean, in the simplest case that you could imagine of each of these situations, this is what the field looks like. The electrostatic field is the first one. It is the electrostatic field. It is the electrostatic field due to a point charge, right, which is a zero-dimensional point, and it's almost by necessarily a scalar, it's just a number, right? And in fact, like all this information here is scalar information. The electrostatic field is caused by a zero-dimensional scalar point source, right? The electrostatic field is a vector whose magnitude is determined by the quantity that I just mentioned, but whose direction is determined by a displacement vector that points from the point source of charge to the point in space of interest, right? Like, okay, the electric field function tells you how many newtons per coulomb are waiting to happen at this point in space, waiting to be exerted on any hypothetical test positive coulomb of charge that might ever end up at that space. The electric field is telling us how many newtons of force would be exerted on each positive coulomb of charge, and in what direction such force would be exerted, right? That's the electric field ultimately is a vector that we can place here that has magnitude and direction, and its direction is determined by the direction of r. That is how far away you are and in what direction from the point source. So r points from the source to the field point, from the source of the phenomenon to the place in space that we're interested in. That's what r does, right? Okay, and r, without r, this whole concept is meaningless. This whole concept of field is the impact of some stuff over here in space on any and all other points in space. Okay, so a field function is always necessarily dependent on the variable vector r arrow. Okay, well, same thing's going on with magnetism. Magnetism is the simplest a possible way to model of a field that seems to kick in and occur at some point in space, at any and all points in space, from a bit of current. Okay, the first equation has no differentials in it because it's already about a point. The second equation is saying, no, for magnetism, we need a charge in motion. We need either a little bit of charge in motion, or if you want to think of it as a little bit of current length. But either way, what we need is some flow that has direction, i.e. current. That's what produces magnetism. Magnetism is a field that will be produced at any and all points in space, some displacement r, right? Again, in both cases, r means this means how far away and in what direction is the point in space we're looking at. So each field depends on R, but the electrostatic field depends on R being applied to some point of raw magnitude, what we call like a proton or electron. The magnetic field is the concept of R being applied to something that itself already is a vector with direction. That is the bit of current, IDL. Both have to be fields. A field has to be a vector. So what the magnetic field is, and again, it's expressed as a differential because we want the simplest possible, the smallest possible case. And up with electricity, we already had it just by definition of putting a point there. So this second equation is saying the magnetic field that results, the vector that tells us how fast and in what direction some flow is going and where and in what direction we're standing in relation to that. The vector that resolves, that measures the relationship between those two vectors must itself be the cross product of those two vectors. In other words, each field, well, I'll say this. By definition of field, didn't mean to do that, sorry. Each field is the simplest okay, field lines are conveying a difference that makes a difference, right? The field line, the idea that a field from a point are radial lines that point out in all directions. The idea there is that the field points equally in all directions to the extent that space is equal in all directions. But the field line, what it's carrying is any asymmetry or any non-similarity represented in the source of charge. So in other words, the shape of the charge, whatever extent in which and manner in which it's asymmetric, is what turns the otherwise fully symmetric field lines into something only partially symmetric. If the charge configuration has one-dimensional asymmetry, then the field lines have one-dimensional asymmetry, et cetera, is what I'm trying to say. The field lines are the simplest possible expression of the shape of the source. So when we had a point of charge, electric field lines emanate out from a point source. Magnetic field lines curl, loop around a current source. Why? For the same reason that electric field lines spoke out from a line of charge, because a line of charge has 1 degree of asymmetry. So the field lines have 1 degree of asymmetry. They don't radiate, they spoke. Magnetic field lines would therefore also spoke if they were caused just by a line of charge, but they're not. They're caused by a line of charge with direction. They're caused by a vector going in a certain direction crossed with a vector representing wherever you're looking at for the field. So there's only one axis left that the field could possibly act on, and it's the axis perpendicular to both, right? And the positive direction for that axis is determined by the right-hand rule. So if a field line goes like this, it means we're looking at the field line above here from something that went like that, etc. So field lines loop around lines. So what this ultimately means, and then, by the way, what's the purpose of all that? Like, who cares? The point of an electric field is it exerts a force on a receiving charge. The point of a magnetic field is it would exert a force on a receiving current, i.e., right? Oh, sorry. Right? If the point of the electrostatic field is that since the electrostatic field was defined in the first place to be net electrostatic force per unit charge, right? The electrostatic field was the thing created by one source, and it becomes a force when it is exerted on a second object, the receiver, right? The test charge. So field times receiving amount is force, right? Just cross multiply back. Well, same thing with magnetism. The magnetic field caused by one current is the thing that would exert a force on some second current. So similarly, like the magnetic force is going to be the magnetic unit, so to speak, times the magnetic field. But we have to be careful again, because up here with the electrostatics, it was no problem. The force was a vector being produced by simply a vector multiplied by a scalar. But here again, the magnetic field is a vector, of course, and the current that's causing it in the first, or that's going to receive it here, is also a vector. So this must be a cross product again. So what happens is, we are saying ultimately, in the simplest possible case of magnetism, or the simplest observable effect of magnetism, you have one current going like this, and another current nearby going in the same direction, let's say both parallel, right? The one above will cause magnetic field lines that loop around it, so that, for example, at this point right here, the magnetic field due to the current above it, do the right-hand rule. My fingers point along the current. If I want to look at some point R below the first wire, like let's not even have the second wire yet. Let's just look at a wire. A wire is carrying current that's going across the board here, and I'm interested in what's happening, what kind of magnetic field is being produced by that wire at a point beneath it. Well, like the magnetic field will be meaning the direction of the magnetic field, the direction is obtained by looking at IDL, putting my fingers along it, crossing it down to R. So I put my fingers point along the wire, curl them down to R, and my thumb points into the board. So the magnetic field right there at that point below the wire would point into the plane of this blackboard. Above the wire, it would point out. Like in front of the wire, it would point down. The magnetic field loops around the wire like so. Okay, we already kind of said that. But now what does that mean? It means now if I put another wire in, so that first wire was like the source current. Now let's say I put in another wire, another current somewhere nearby below it running parallel. We'll call that I test. I receiver, right? So I don't care really if it's the same magnitude. I could call it I1 and I2, it doesn't matter. And they could be the same magnitudes or not, but the point is, let's say they're in parallel directions, right? So now this current is dunked into the field of that current above it. What does it experience? It experiences a force. A force, it experiences a magnetic force because it is a moving set of charges in a magnetic field. Right? Just like a test charge experiences an electrostatic force if it's in an electrostatic field, a moving charge flow will experience a magnetic force and therefore an acceleration. If it's in a magnetic field, what's the direction? Well, cross product. Here we have, I put my finger, so I'm asking, what's this magnetic field at this, how can I say this? This wire is below that one. So it's this second wire, the second current. So it's experiencing magnetic field into the board, we just said, like there's magnetic field everywhere here. I mean, it's stronger and stronger as you get close to that top wire. As we get farther and farther away below the top wire, the magnetic field gets weaker, but it's always pointing in the direction we just figured out by the right-hand rule. So we've got this wire dunked in a magnetic field. The wire, I put my fingers along the vector of the current carrying wire, my fingers go along the current, and I curl into the field. I curl my fingers into the page, because that's what the field is doing, and my thumb points up. So the force is up. So what I'm saying, it's like a long, convoluted, it's really weird. There's a medium now, so to speak, right? When it turns out that when one wire is pulled towards another wire, we say it's because of magnetic force. When one current, is pulled towards another current, we attribute that to magnetic forces being exerted by magnetic fields that each one of the wires exerts. But this weird thing about the magnetic field is if it works like a field at all, it actually doesn't point in any direction that one might expect. It doesn't point in the same direction as the wire, and it doesn't point in the direction that you walk away from the wire. In fact, that's the whole point. It necessarily points in neither of those directions, because the only way the information could be equally taken into account from both of those axes, the only way the magnetic field could be determined both by the current direction itself and the direction in which we're looking from the current, the only way both of those vectors have equal weight in this dual measurement, this relationship, is if they were crossed, if they yielded an answer equally far from both of their answers, their sizes, i.e. 90 degrees from both. This is how cross products works and why they work. So the magnetic field underneath one wire points into the board. Then a second wire is put into that magnetic field, and a magnetic field pointing into the board, acting in which a rightward pointing current is immersed. The rightward pointing current will experience a force up toward the top wire. Okay, it's like there's an extra big weird step of right turns in there. It's all because the magnetic field is not caused by a point. It is not the multiplication of a scalar by a vector. It's caused, even in its simplest case, by a vector, by a line with direction. And so it itself, the magnetic field, is a cross product of one vector with another. The magnetic field must point perpendicularly to whatever causes it, and then it'll exert a force perpendicular to itself on whatever's experiencing it. Therefore, we said this last time, but now to start comparing the two really directly and seeing how they affect each other, we have for the electric field, Gauss's law. For the magnetic field, what I call the Nobi Flux Law. The second one is really called Gauss's law for magnetism, but I call it the Nobi Flux Law, meaning Nobi flux, meaning just as Gauss's law says, the total amount of electric flux through any closed surface, through any container that you ever consider in space, put any container anywhere in space, ask how much total electric field is fluxing through that container. And the answer will be fully determined by whatever charge you happen to have captured in that container. Not how the charge is shaped, not any charge outside the container, and not the size of your container and not the shape. Just whatever charge you capture will determine the total electric flux through the walls of the container. What really is flux? The best way I could say flux is number of field lines. Like if you can picture field lines, and if you can picture that the density of field lines represents magnitude of field, like the number of field lines per unit area on a picture represents field strength. Flux by definition is field strength times area. So the reason we care so much about flux is When you draw a picture, when you look at field lines, you can't see how big the field is by the number of lines or the size of the lines or anything. They go on forever. We say that how thick the lines are, how dense they are, how many there are per unit area is the field strength. So if we multiply that by area in our minds, and we always think about flux, then the areas cancel out. Flux is field lines per area times area. So every time I talk about flux, I'm really just talking about the number of field lines crossing through some area. Any container you bring anywhere in space, the total number of field lines that will pop through that container is determined 100% by how many point charges, how many coulombs of charge are inside the container. Each point charge radiates out a number of field lines, and field lines start at positive charges, or they come in towards negatives. With magnetic flux, put a container anywhere in the universe, the total number of field lines that will come out of that container, net, like if out means positive, and if we subtract from that any that come in, the total number of field lines that will ever emanate out from any container anywhere in the universe, the total number of magnetic field lines that will emanate out of any container is net zero, because for any line that ever comes out, it will necessarily come back in, because all magnetic field lines are closed loops. They don't emanate from sources. They don't land at sinks. Magnetic field lines encircle vectors. Okay, vectors that go on forever, if you like, okay? This is a powerful statement about magnetism. It means there's no magnetic monopole the way there is a such thing as an electrostatic monopole. But it's really powerful, but it's always true. So it means that we can never use magnetic flux in order to predict or compute the amount of magnetic field strength somewhere due to any current configuration. Like to figure out electric fields, we use Gauss's law, the top law here. The equivalent of it applied to magnetism is the second law here. It's a law, it's just as true as the top one, but it doesn't have any computational power because the answer it yields is always zero. So what do we do in order to compute magnetic fields? We bear in mind exactly what we just said, which is the whole issue is that magnetic field lines are closed loops, again, because they're formed from cross products, really, in space. So in order to deal with that fact and be able to compute or predict them as easily as we do electric field lines, we have to embrace that fact in order to compute. Magnetic field lines are closed paths. Therefore, they don't net flux out of surfaces. So we can't use closed surfaces in order to compute magnetic fields. Because they're closed paths, we cannot use closed surfaces to get anywhere in understanding them. What we use instead is closed paths, because that's what we are. That's what they are. In other words, the law Ampere said, oh, right, yeah, they're closed lines, these magnetic field lines. They're not emanating out from points. So instead of looking at any closed container in the whole world and trying to figure out something, let's see if we can make any claim about any closed path integral of the magnetic field anywhere in the universe. Instead of a closed surface, a flux integral, let's look at it directly at a closed path integral magnetic field. And it turns out it works just as you would expect. It's equivalent to the Gauss law result. The closed, if you walk around any closed loop, the total amount of magnetic field that you'll pick up is entirely due to however much current you were encircling by that loop, because that's what causes magnetic field. In other words, we have I enclosed instead of Q enclosed, and we have the magnetic constant instead of the electric constant. And it happens to be multiplication instead of division for the same reason that the mu naught is in the numerator of the constant rather than the denominator. It's just all to keep things consistent. But this is just like Gauss's law, but for closed. This says the total amount of magnetic field that you find going around any closed loop path, which i.e. a loop, is fully determined and fully equal, modulo constant, fully equal to all the amount of current that you find enclosed by that loop. Now, what does enclosed mean? There is a technical point, which I will get to, but largely, basically what enclosed means is whatever current flowed through the open area bounded by the loop. In other words, if your loop is going like this, we're counting all the current that goes through perpendicular to a plane, like the disk bounded by your circular loop. In some cases it's intuitive, in some cases it's not, but that's the law. Now we're almost somewhere. So far we have this. So that's the law that you use to calculate magnetic fields. We're almost. So if we're trying to develop a picture in our minds of electrostatic fields versus magnetic fields, and we so far have these relationships, and we would be done. Okay, so we have like three closed integrals. Like there's starting two. We have a statement about the electrostatic field and now two statements about the magnetic field, because the first one turned out to be really important and universal, but not computationally helpful. So we have a double integral. We have like all the electric field through some closed area is equal to all the charge within the volume enclosed by that closed area. So we have like three. So in other words, okay, in the first law, it's like something about the closed two-dimensional region that is bounding a unique three-dimensional region. And then in this last law we just did, it's something about the closed one-dimensional region bounding some sort of open two-dimensional region. Okay, and we would be done. This would be this relationship of the electric fields and the magnetic fields, except it turns out there's this discovery, and it's a discovery. I mean, it's a discovery that comes after Orsted's discovery, and it sort of makes the Industrial Revolution possible. And it's a discovery by Michael Faraday, who was a Scottish high school chemistry teacher, and for whom our whole concept of field lines and flux really owes a great debt. I'm going to see how he is tinkering around the lab and sets up a situation which has an expected result in one particular case under one condition, but what's unexpected is that the result turns out to be hold steady even beyond the one understandable case. So let's try to draw this as fast as I can. So basically, Okay, just picture a uniform magnetic field coming up from the lab table, let's say, like, because you made some large solenoid that produces this or whatever, and you oriented it the correct way. So you've got like magnetic field lines coming up from the lab table, let's say. So you've got something like this, like a square, like uniform, meaning there are parallel lines, they're all the same density. So we're considering some, oh, sorry, up from, I should have set down, but all right. So up, we're in this magnetic field. And again, this is pretty much the last thing. But I might have to do this into some parts too. Okay, these are all supposed to be represent like dots coming out, magnetic field lines coming out of page, because we're looking down bird's eye view on the lab table. Now imagine that we create the following in this. We put a rail and a rail made of metal and a rod made of metal and a resistor made of metal. Okay, so this is like a rail, this is a rail, this is another rail, and with a resistor R right here. And this thing is a rod, length L. Okay, so metal, 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 and a metal rod. So 4 things of metal connected. So a closed loop of metal. Now nothing. Now there's no battery or anything like that. So there's a bunch of protons sitting in this metal, but there's also a bunch of electrons, and they're all just sitting there as they should in macroscopic, stable, balanced material, which this is. So this is conducting, right? So this is stable conductors. But imagine that due to an external force, we can move this rod back and forth. We can slide it along the rails. We can give it, due to an external input of energy, we can give it some velocity. And let's even say we can make that velocity constant. So we can push the rod in a certain direction, let's say to the east, to the right. So we can slide this rod along to the right, okay? And that's what Michael Faraday did. He deliberately moved a metal rod through a magnetic field. So let me say there's a magnetic field here. There's a magnetic field because of some large apparatus that we immerse this whole setup into. But there's a magnetic field, but it's constant. I mean, constant in space and time. It's just like an amount of magnetic field strength just sitting here, okay? Now, magnetic fields don't affect masses, right? You could put a mass in magnetic field, but it doesn't exert a force on it. You know, gravitational fields exert forces on masses, and electrostatic fields exert forces on sitting charges, net charges. So if there were any net charge here, an electrostatic field would do something to them, but we don't have an electrostatic field. We have a magnetic field, magnetostatic field. If it's going to exert a force on anything at all, it would be on moving charges, right? We would have to have moving charges for the magnetic field to exert a force on it. Okay, so right now it's just a magnetic field sitting there, and there's just a bunch of equal and opposite charges like all throughout the metal. But then we start moving the rod. So now we are taking a bunch of protons and moving them to the right. We're also taking a bunch of electrons and moving them to the right, for sure. But that's significant because we're now creating current. Like, in fact, if we're moving all the protons to the right, that's, but yeah, anyway, we're moving a bunch of protons to the right. So, and we're doing so through a magnetic field on purpose. We're going to move a rod of metal through a magnetic field, and as Faraday predicted, as you would predict, if the rod of length L moves at V, you know, constantly through B, then then we are moving a bunch of protons through a magnetic field, and therefore the magnetic field will exert a bunch of a force on those bunch of moving charges. Like they had to be charges to experience anything at all. They have to be moving to experience a magnetic field. And in fact, they have to be moving with some amount of perpendicularity to that field for the cross product even to obtain. But they are moving, the rod is moving to the right, and the field we're saying is going is out of the plane of the board. So we do the right-hand rule. Our fingers point to the right, our fingers point to the right, and the magnetic field points out of the board. So my thumb points down along the rod. Right, the plus charges are going like this in a magnetic field coming out of the board, so they're pushed down the rod. Similarly, you have electrons. There are electrons that are being pulled the other way, but if we do electrons, we have to do our left hand. So we have electrons going that way in a magnetic field that I can't do my left hand. The opposite happens to the electrons. All the protons are pulled down the rod by the magnetic force, by the magnetic field that's coming out of the page. And by the same logic, by the right-hand rule, all the negatives are pulled up in the rod. So you have current flow, you have net positive flow through the rod, and the rod is attached to other rails that are attached to themselves. So suddenly, what you get, as he expected, as he was intentionally trying to set up, you get current flow through this rod. That's sort of okay, sorry, I think that got cut off, but can we still hear? Okay, so the result is we suddenly have current where we didn't before. We suddenly have current with no battery at all. Why do we have current? Because we deliberately moved the rod. So we didn't get something for nothing, but the point is now due to a mechanical source of energy, by some pulley or whatever that moved this rod, that got converted and resulted in electrical current. We just got electrical current without a chemical source, without a voltaic cell, without a chemical source of energy. We instead got current through a magnetic source and ultimately through a mechanical source of energy. Kind of exciting. And the exact relation that he got, the amount of current, the equivalent, so okay, we get this current with no battery. The question is, how much current do we get? In other words, the current that we do get, how much of a battery would we have needed to get that equivalent current? Like, in other words, okay, whatever current we get that we're getting now by moving a rod, instead of by putting in a chemical battery, whatever current we get is regular everyday current. Once we get it, it's measurable in good old standard amperes. but let's call it induced current to designate the fact that this is everyday current once we get it, but we got it the special way. We got it by moving a rod through a magnetic field instead of by a voltaic cell, by a virtue of a chemical battery. So we're going to call this induced current. What I want to solve for quickly, and this is like the last thing we have to solve for, but believe me, we do, in order to get extra credit in life and on the exam and in the course. What I want to know is, what is the voltage of the battery that we just saved ourselves from having to buy if instead we were willing to push this rod? Okay, what is, well, remember, voltage is electric potential, electric potential difference. Electric potential difference is electric potential energy per charge. That means work that would be done by the electrostatic force per charge. So we want the voltage. So we want let's look at that rod. Remember, what happened in the rod is all of a sudden the positives went down to the bottom of the rod and the negatives went up. So let's look at how much work it would take to move a charge against the electrostatic field, or the field line that results in the rod. Let's see how much work it would take to move a charge through that field. The answer to that question is what we mean by the potential difference between the two ends of the rod. Okay, well, with the force that's experienced here, the electrostatic force that's exerted here, I don't know, like it's an equivalent electrostatic force, just like I'm finding an equivalent voltage. Like there is no actual battery there. I'm finding the voltage that would have been necessary or produced by a battery had I put a battery there. Similarly, so by the same reasoning, what is voltage? It's the amount of work you'd have to do across the electric field that is there. Well, there is no electric field along this rod. There's a magnetic field doing force, so that's producing the equivalent phenomenon. So in other words, I'm going to say, like the only force I have to work with here is the magnetic one. Okay, so I'm saying. Oops, sorry. Okay. Well, that magnetic force is ILB, or in other words, sorry, one thing I've dropped by accident. I'm sorry, I dropped one thing entirely. This entire time, from electric field, I meant to go to electric force per charge. I'm sorry, force per charge. Field is force per charge. So if I'm trying to integrate across the field, I'm integrating force per charge. So this is FB over Q. Excuse me. Okay, so on the next page. Okay, so what is the magnetic force? The magnetic force is QV cross B, which is the same thing. All divided by Q. Now, V cross B, that means VB sine theta. But theta is definitely 90 degrees here. The angle between the V and the B, the angle between the flow of charge itself and the magnetic field itself, they are at 90 degrees. So QVB sine theta is the same thing as QVB times 1, which is QVB. So we have. Let me go on the next page. Okay, and the q's cancel out. Okay, and so now we have the integral of VB with respect to DL. We're integrating along L, like we're integrating along a path because we're trying to figure out work done. So we're integrating a force, but per charge, so that we can get potential rather than potential energy. So we're integrating along DL, we're integrating the function VB. V and B are constant along L. Like the velocity of the rod doesn't change along the rod, the magnetic field does not change along the rod. So we have the integral from 0 to L of DL, the integral of L, like the full length of the rod. In other words, okay, what does all this mean? The induced EMF, the induced voltage, the equivalent battery that you create by not having a battery at all, but by just having a loop of wire, not loop of current, but loop of wire, right, that just has dead charges in it. If you move part of the wire in the proper way through a magnetic field, then you get this voltage, this induced voltage, which is exactly equal to the speed of the rod times the magnetic field that you're in times the length of the rod. All those three things together, like the bigger any of those quantities is, the bigger the EMF is. Now, it makes sense. I mean, if you let it sink in and think it through. Faraday set this all up because he predicted something like this would happen because he did understand. He was moving a rod through a magnetic field, so he expected the current. But the crazy thing is that it turns out that it's not just true in this case, it's true in any case. And there's no, I'm not saying this logically should be true, but it turns out that whether he moved the rod through a magnetic field or he moved a magnetic field past the rod, or whether he changed the strength of the magnetic field or changed what turns out to be the area enclosed by that loop, no matter what combination he did, this VBL result, if you step back and look at it a different way, always obtained no matter what, and not for any obvious reason, but just because it did. In other words, all this reasoning shows that this would make this, that you'd get a voltage in this one case, but instead of writing VBL, we could write BLV. I mean, like, duh, like multiplication is commutative, but what's BLV? If I look at BLV, if I step back from it a second, BLV actually looks like something familiar. BLV, if I think about it, like, remember, we're talking about all this, we're doing all this stuff with magnetism with closed loops because closed surfaces didn't get us anywhere with magnetism. The flux through a closed surface was always nothing due to the nature of magnetism. So the flux, the total amount of field lines through an area, didn't do any good for us when our area was closed. But look, what we have here, bounded by that loop, like I know that this is a wire loop. I can ultimately imagine a circuit going through this wire. Where'd it go? The reason I can even imagine current running through this wire once it gets started is because the wire does form a closed loop, if I ever get back to that page. Like there's a square of white here that we can imagine current going around and around once we have a reason for it, right? It's a closed path. We know it's closed because it's bounding an area. I can picture the square within the perimeter of that square, and there are magnetic field lines through that square. There's magnetic flux in that square. Now, there's never any net magnetic flux through a closed area, but here we have an open area that most definitively has magnetic flux through it. And in fact, Now, in fact, if I write down like this, if I think about it, or even, sorry, like this, what is that? That is and that is right. I mean, a constant times a derivative is the same thing as the derivative of something times a constant, right? So actually, and what, and at any given point in time, at any given point in time, what this expression here is, well, at any given point in time, at any moment of time t, L times X is a length times a width, so to speak. It's the area of the loop, right? Like the longer X is, like X is like the position of the rod that is changing every moment in time. The farther out the rod is, the farther out the width of this whole rectangle is, right? L is one dimension of a rectangle, like the length, and X is like the width of that rectangle. So what we really have here if you really think about it, is we have voltage that is produced by the time rate of change of the total magnetic flux going through the area bound by the loop. Complicated thing to say, but I'm saying the rate at which magnetic flux, in other words, we move the rod, what we do is we change the area of some rectangle bounded by the potential circuit of which the rod is one link. How can I say this? So at any moment, we have some rectangle. Whatever amount of magnetic field lines are penetrating through that rectangle, that's what we call magnetic flux, like the number of magnetic field lines flowing perpendicularly through the areas, through some area, in this case, the area of the rectangle. So at any given moment, there's a total magnetic flux going through that rectangle. The rate at which that total magnetic flux is changing, in this case, the rate at which the rectangle itself is changing in time and thereby opening up more and more magnetic flux, that rate is what I have written right here. ddt of BLX is right? I'm saying in this case, the rate at which the magnetic flux through this open area, magnetic flux through a closed area is always zero. But here we have an open area, the area bounded by the closed loop of metal, the closed path of metal. The rate at which that open rectangle grows is precisely the amount of voltage that we get due to this configuration without any battery at all. Okay, that's what we're saying here. And when I say voltage, I mean potential difference, right? Potential difference is the integral of field from one place to another, okay? But what's the one place to another? In this case, the one place to another is none at all. There's no anode, there's no cathode. There's just this loop that we're stretching through a magnetic field. And what we're finding in this case is that the voltage around that loop, the potential difference around that loop seems to be equal in magnitude to the rate of change of, the rate of change, and this should be a double, the rate of change, not of magnetic flux through the area bound by that loop. A mouthful, but that's what we seem to be finding here in this case. Now, in this case, I'm saying something in a very elaborate way, but I'm just saying, oh, we got some voltage here by moving a rod through magnetic field. By the way, that's a generator. That's the Industrial Revolution right there. Like, it's a big freaking deal technologically, but also conceptually, it's a big deal that by moving a rod through a magnetic field, we get electrical current, ultimately. We get voltage. We get voltage around a loop. We get a circuit with no battery. The exact amount of circuitry, we get the exact amount of voltage we get around this circuit, the left side, is precisely equal to the time rate of change of magnetic flux through the area bound by the loop in which we are looking for voltage. Okay, what's crazy is that this thing turns out to be always true, no matter how you do it. If you've got some area that has magnetic flux going through it, if you change that amount of magnetic flux in any way, change the area or change the magnetic field strength or both, you will induce a voltage in the loop bounding that area. Always, it turns out. No reason why that should be. I mean, there is ultimately, but there's no obvious reason why that should be. Okay, and the direction of magnetic field, the current of flow that you get always goes against the right-hand rule, because otherwise you'd have a perpetual motion runaway machine. It's a total surprise that it's always true, but it's very heavy. It's the last of 4 laws that I want to have in your mind if you want to really put this whole package together. I'm going to just explicate these 4 laws on the next page and stop there in a moment. There is one, I have to put them together in one last talk, but this is the finality of any content of any of the pieces that then get put together for the final puzzle. But okay, there's going to be, then this is the last law, and I've just already written it, so nothing new, but the last law is called Faraday's law, and it completes a picture of 4 laws which together make electricity and magnetism as a set theory. I mean, there's one more thing to say about it all, but there's 4 laws, 2 about the shape of the electric field, 2 about the shape of the magnetic field, and they are these, and this is where we're stopping for now. If nothing else, what I want to end your minds with for the moment, or what I want you to see, is that although the right side is a bit of a staggered, not perfect pattern, the left side is like a perfect pattern, the left side of these 4 equations. The right side needs a little cleaning up, which is why there's one last thing to say, but the left side is 2 laws about the shape of the electrostatic field and 2 laws about the shape of the magnetostatic field. Similarly, it's 2 laws about closed surface areas, and it's 2 laws about closed paths. And the results are the right sides. That's the magnetic and electric field in and of themselves, and the 2 constants, epsilon naught and mu naught, you don't have to memorize, but they're assumed to be this. Okay, I'm going to stop right there.